Okay, everybody, so we're recording here. Okay, so let me just highlight this. I'm able, let's see, there ought to be a feature that allows me to highlight. There we go. So one of the most important ideas in calculus is that as we zoom, so we're talking in section 11.4 about tangent planes and linear approximations. So remember in calculus, if you zoom in towards a point on the graph of a differentiable function, the graph becomes indistinguishable from its tangent line, and we can approximate the function by linear function. So essentially they're saying that if you if you have a very small neighborhood about a point, the tangent line will essentially approximate your function, your curve. That's calculus 1. How many remember that from calculus 1? And therefore the line could be a good linear approximation around that point. Charles remembers that. You know, and the idea is that Yunu remembers that. Good. And the idea is you can approximate function values by using your linear approximation, your tangent line at that point for values that are near the point. Here we develop similar ideas in 3 dimensions. In 3 dimensions, as we zoom in towards a point on a surface that is a graph of a differentiable function of 2 variables, the surface will look more and more like a plane. And therefore, we can approximate the function by a linear function of 2 variables. Okay, that's the idea here in section 11.4. So to give you an idea of this, let me just go down to this little picture here, figure 2. So here you have an elliptical paraboloid, and you have in figure 2, you have just an elliptical paraboloid, and then you have a tangent plane to that elliptical paraboloid at the point 113. Well, so in figure A, you know, there's the picture. Figure B, you're narrowing in on that point 113. You notice the x goes from -2 to 2 and y goes from -2 to 2. And then in figure C, you're even narrowing in more closely to the point 113. And you see how the surface, the paraboloid, begins to look like a plane when you're for points near the point 113. Maybe give me a thumbs up if you see that. Okay, Yunu sees that, and Ellie sees that. Okay, well, great. Well, so and Juliana, and excellent. And you know, the idea here is, okay, well, if we want to find the equation of a tangent plane, how are we going to find that equation? So I think it's worth showing you how they come up. Well, here is the actual, this here is the actual equation of the tangent plane. And the tangent plane, you can see, is dependent on partial derivatives of the function at x and y, about some point x sub 0, y sub 0. So let me show you how they get that. I think it's worth showing you. So they start off here with the picture. They start off here, well, let me start here. Okay, so suppose a surface has an equation z equals a function of x and y, where f has continuous first partial derivatives, and we're going to let a point x sub 0, y sub 0, z sub 0 be on the S, on our surface. Okay, let C1 and C2 be the curves obtained by intersecting the vertical planes y equals y sub 0 and x equals x sub 0 with the surface S. So you see what they have here in figure 1 You see they have two curves, C1 and C2. C1 is the intersection of the surface with the plane y equals y sub 0. And C2 is the intersection of the surface with the plane x equals x sub 0. So you have the intersection of the surface with two different vertical planes, one being x equals a value and the other plane being y equals some value. And those are the curves on the surface, C1 and C2. Now also you see there tangents to the surface at that point P, and they are tangent to those curves. So what we want to do, if we consider those two tangent lines there, there's a plane that contains the two tangent lines, right? And we need to find the equation of that plane. We need to find the equation of that plane. Okay, so remember, maybe let me just bring this up in the whiteboard. So you remember the equation of a plane as a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus c sub 0, and that equals 0. Okay? But you could, of course, then write the equation of this plane as z equals something, right? You could write this as z equals something. And as a matter of fact, if you were to do this, you could do this. You could write, I mean, this is the equation of a plane. Equation of a plane passing through the point P, which has coordinates x sub 0, y sub 0, z sub 0, and has a vector perpendicular to it given by the components a, b, c. So z minus z sub 0, okay, let me just see here now, one moment. We could actually, by the way, yeah, well, let me just see here. I want to just, yeah, so in the book, what they do is they use like big A, big B, and big C. That's what they do here in at the beginning of a section 11.4. That's okay. That's okay. They can do that. And if you were to divide by C, okay, maybe I don't want to do too many steps here at once. If you were to divide by C, so we're assuming C is not equal to 0, you'd have A over C times x minus x sub 0 plus B over C times y minus y sub 0 plus z minus z sub 0 equals 0. Okay, and so z minus z sub 0 would equal negative a over b, okay, times x minus x sub 0 minus b over c times y minus y sub 0. And what we could do now is we could call, well, are there any questions up to this part? Let's start there. Are there any questions? All right, well, what we could do is we could replace this. So all I'm doing is I'm just rewriting this equation in a format that like the book's doing it. So what they're doing here, is they call this A, capital A over capital B, they call that A, and capital B over capital C, They call that B. Do I have an error? Let me see. Oh, man, thank you. Let me fix that right now. Yep, hold on. Thank you. Good catch. Good catch. Yep, thank you. Oh, okay. Just the one. Got it. Thank you. Okay, so they're going to replace these constants with little a and little b. And so z minus z naught, or z minus z sub 0, is going to equal little a times x minus x sub 0 plus little b times y minus y sub 0. Okay, so our tangent plane is going to have this equation. The question is, what's little a going to be? What's little b going to be? Okay, for this tangent plane to our surface at the point P. Well, what they do is, now let me go back to the book. You know, there's our tangent plane to the point P. And so if we focus on the first curve, curve C1, that is the curve that is on the surface, and that curve was cut. If we take the plane y equals y sub 0, okay, take that vertical plane and cut the surface, the cut will look like that curve C1. Okay, so what we can do here is we can do the following. Let me find it right. Hold on, it's here, at least it is in the book. Yeah. So what they do is they say, okay. The intersection of if the tangent plane, I'm going to say this the right way. If we go back to the picture, here's that tangent plane, and the intersection of the tangent plane with the I'm not saying this the right way. Sorry. Okay, so if we were to take the plane y equals y sub 0 and intersect that with the tangent plane, we would get that tangent line t sub 1. Okay, and that's absolutely true. Okay, so, what is the equation of that tangent line? Okay, well, the tangent line is part of the plane, right? It's part of the plane. So we can manipulate the equation of the plane by taking y equals y sub 0 and substituting it in the equation of the plane right there above. If we do that, we're going to get z minus z naught equals a times x minus x sub 0. That's the point slope form of a line, though. What is, this here? Hold on. I don't know what happened here. Hold on. Let me go back here. Okay, boy, if you click on the wrong thing, it can be rough business, huh? All right, let me remove this highlight. All right, so this here, what would the equation of that tangent line be? It would be z minus z naught equals a times x minus x. Sorry, the equation of that tangent line would be z minus z sub 0 equals a times x minus x sub 0. That's the point slope form of a line. Point slope form of a line with slope a lying in the plane y equals y sub 0. But we know the slope of that tangent line is the partial derivative of f with respect to x, at the point x sub 0, y sub 0. Therefore, A is going to equal x sub 0, the A will equal, let me highlight it here, the value of A in the tangent plane will equal the partial derivative of f with respect to x at x sub 0, y sub 0. So now we've solved for A. And if we want to solve for B, all we need to do is we go back to the picture again. Okay, in B, here, you got another tangent line, the second tangent line, which is the intersection, it is the intersection of, well, no, hold on, let me say it the right way. Yeah, if we take the intersection of the plane x equals x sub 0, okay, with the tangent plane, we're going to get that tangent line t sub 2. The tangent line t sub 2 is moving in the y direction, right? It's moving in the y direction, okay? And we can now, but that tangent line t sub 2 is also in the equation of, it's also part of the, it would satisfy the equation of the plane. So the tangent line t sub 2 meets, for that tangent line, x equals x sub 0. So we can substitute x equals x sub 0 into the equation of the tangent plane, and then we'll be able to get the equation of the tangent line because of that constraint. And so when we do that, it will be determined then, that B, hold on, it'll be determined that B equals the partial derivative of f, partial derivative of f with respect to y at x sub 0, y sub 0. And therefore, you get then the result below. That proves this result. Okay, that proves that result. Are there any questions on that? Okay, so I mean, how many remember like in let's see here, in calculus 1, this equation here. How many recall that? Yeah, this is just a three-dimensional analogy to that. This particular, hold on. Yeah, this particular result. So let's look at an example. Absolutely amazing. Absolutely amazing. So let's look at an example here. I'll go down here. Oh, well, look, they even mentioned it. My gosh. They even mentioned it right there. Look at the similarity. Maybe I can have them both here. Hold on. We'll see if I can have them both displayed. Yeah. Note the similarity between the equation of the tangent plane and the equation of the tangent line. Okay? So you're really learning beautiful stuff here. Are there any questions so far? Okay. Good, you do. Good. Well, let's proceed forward here. So in example 1, they want you to find the tangent plane to this elliptical paraboloid at the point 1, 1, 3. Well, okay, so all you do is compute your partial derivatives with respect to x and y, evaluate those partial derivatives at x equals 1, y equals 1, and then plug those, and then just apply the formula for the equation of the tangent plane, and and this is going to be your answer. Okay. One moment here. One moment. Okay, now let's go ahead and look at an example here. Okay, take a moment to copy the example down. Okay, so here we have this paraboloid. Okay, this is a function that represents a paraboloid. And we want to approximate the function at the values 1.1 and 0.95 using the linear approximation of this function at x equals 1, y equals 1. So you notice the linear approximation, okay, we're picking, an x and y value that's pretty close to 1, 1. Because we know linear approximations get worse as you move away from your point of center, so to speak. Okay, so why are we using 1, 1 as our point to derive our linear approximation? Why are we using 1, 1? Why are we using these integer values? Can anybody tell me offhand? Well, Ian, it is close to 1.1 and 0.95. I like that. And it's also in x equals 1, y equals 1 is easier. That's right, Ellie. So, well, we're trying to approximate this function, right? And this function, if we were to substitute in 1.1 for x and 0.95 for y, it would involve a little bit of work. We'd have to square and pretend. You got to kind of pretend that you don't, that you're working out by hand. Okay, just pretend. Even a computer has to do flops to do math operations, right? So you wanna have your approximating function be at nice values, and 1, 1 are the closest nice values to the coordinate 1.1 and 0.95. So that being said, they always will normally give. Well, I want to be careful. It should be obvious what the nice values are going to be in a problem. Let's go ahead and okay. First of all, we compute our partial derivatives with respect to y and x, or x and y. And then about 1, 1, I apply the formula and come up with the equation of my plane. Now let me give you a moment to catch up here. You see here, f of 1, 1 is easy. This is easy to evaluate. This is easy. So what, you got to think, remember why mathematicians came up with these approximations. They had to find values of difficult functions where it required a lot of work to get the answer. And they say to themselves, well, if I use a linear approximation, linear approximations it's pretty easy to compute values with linear approximations. I don't have to, take the sign of anything or exponentiate anything. It's pretty easy because, it's just, in this case, an equation of a plane. And so, you're using the linear approximation rule should give a very good estimate of the function, so long as you're using the linear approximation to estimate function values that are close to the point that you're using. Okay. And so we end up getting 4x plus 2y minus 3 in our answer here. So our function about the point 1, 1, okay, and let me emphasize that, about the point 1, 1, our function is approximately equal to 4x plus 2y minus 3. Okay, so maybe I'll write this. F of xy is approximately equal to that it's approximately equivalent to that plane. So now we can evaluate the function at the point 1.1.95. And you see the computation is easy to do. And if it's easy to do for a human, it would be easy to do normally for a computer, right? Because humans can sort of easily multiply, add, subtract, and divide, right? That's how many have heard of arithmetic flops for computers? Like a flop's a math operation. Charles has heard of that. Okay, so this is no problem. This is no problem evaluating that. Malik knows what I'm talking about. Absolutely, it's no problem for us to evaluate this here using our linear approximation. We can evaluate 4 times 1.1 plus 2.95 minus 3. That's easy to evaluate. We don't need a calculator for that. We get 3.3. So the value of our parabola, the function value, when x equals 1.1 and y equals 0.95, is about 3.3. Now the exact value is 3.3225. So we didn't do too bad, right? We didn't do too bad. We're correct to the 10th decimal place. Okay, take a moment to copy that. Okay, now I want to show you something. So remember, like, how many remember from, so we're doing a linear approximation here, but how many remember from calculus 2, like, could we get a better approximation than a linear approximation, you think? Think back to calculus 2. Are there quadratic approximations and cubic approximations? To show you what I mean here. There absolutely are. And how many remember like Maclaurin polynomials, Taylor polynomials in calculus 2? Absolutely, absolutely. Well, let me show you what the equivalent would be here in calculus 3. Here's a Taylor formula to evaluate a function or to approximate a function value at the point A, B. This is what, hold on, let me get the, zoom on, click on your right, click the zoom key if you need to, but take a look at that. So look at the second, so, here's like f of AB would be like f of x sub 0, y sub 0. Okay, and then you have a linear combination of the first partial derivatives, okay, evaluated at x sub 0, y sub 0. So this is so far what you studied tonight. But now here's an additional term. If we want a quadratic approximation, what derivatives need to be used for a quadratic approximation? What order are these? They're second order. That's right, Ellie. Second order partial derivatives. So you might wonder, why am I computing these second order partial derivatives? Where would they be used? Oh, okay, here's an example of where they could be used. Okay, you could program this in a computer, right? And then look, if you want a third, if you want to get a third order, what do you call it? Like a cubic approximation, you need to go out to the third order partial derivatives. Okay. How many think that's absolutely amazing, this kind of formula? Uh-oh, I'm not getting too many responses. It's pretty cool. And you're only going to have to go do linear approximations. But I'm just making you aware that it's pretty deep, but you know, everything you're doing is for a reason. Okay, all this math you're learning is used in applications, and you know, so okay, let's continue on in the book here. Let's continue on here. All right, one moment. Okay, so we looked at a little example here, and I want to look at a few more things here. Linear approximations, we just discussed an example of that. Okay, and then how many recall differentials? Hold on, class, let me find this formula that I want. How many recall differentials in Calculus 1? Where you have delta z and dz. Well, you would have delta x, and you know, look at the picture. Thank you, Charles. Look at figure 7. So here, you know, you have your differentials, delta x, delta y, delta z. Okay, but so I don't know. Differentials normally should be talked about in Calculus 1, but basically. What we're interested in is something called a total differential. And there's a formula for that. Okay, a formula for that. Hold on here. Let me find it here. It's here. There we go. This is what's called a total differential. Okay, a total differential. And there are applications of this. You'll see some applications in your homework, and don't worry, there are help aids, watch it videos, because you know, I think you can manage this okay, even if you haven't necessarily seen it. The point is if you look at in the homework, you'll see some applications of differentials. It's going to be very simple. Do not worry. But I think differentials are better understood by looking at concrete examples, seeing how they're used. So in your homework for section 11.4, you'll have an example, like for instance, if you take measurements. Okay, if you take measurements for something, like maybe you're trying to take measurements for a box. Okay, and you have possible errors in your measurements. Well, then can you estimate the maximum error in calculating the surface area of the box? You can estimate that error using differentials. Okay, and so that's where they're useful. Okay, and I have some nice examples that you can look at, and there are, well, some nice exercises that you can look at with help aids in your homework. So I think you're going to be fine. I want to move on. Here. Try to give you a little time to work on this section 11.4. So let's move on here. Yeah, using differentials to estimate an error. That's example 5. So, all right, but let's move on here. Okay, so here, what if you have a function of 3 or more variables? Well, here's the linear approximation for a function of 3 or more variables. So it's a natural extension. It's a natural extension, and you know, I think it's pretty intuitive. And in terms of a differential, if you had a function of 3 variables, okay, your differential would be defined this way. Okay, so again, when you look at some examples in your homework with the help aids, you'll feel better about this. All right, let's move on. Let's move on. Okay, this is what I want to get to next. Tangent planes to parametric surfaces. Okay, so remember in section 10.5, you learned about parametric surfaces and how you could take a function, a vector function of two variables, and let the variables u and v vary over some domain, and then the vector function, the vector function, which is a vector, the tip of that vector will scratch out a surface in three-dimensional space. So, for instance, a cylinder, you would use a vector function of two variables to represent a cylinder. So the thing is, well, you know, what if we want to find a tangent plane to a particular parametric surface? Okay, how would we do that? I mean, we can find a tangent plane to a function of x and y, but what if we don't have a function of x and y? What if we have, like, you know, a cylinder or something like that, a parametric or a helix? You know, how are we going to find a tangent plane to a helix? Well, the way they show this is basically in Figure 9. Okay, you have here your domain D, of your u and v parameters, and again we set u and v fixed. When we set u to equal u sub 0 and v to equal v sub 0, that's going to then give us a point p sub 0 on the surface. Okay, and that point p sub 0 on the surface, you'll have if you let the v, like if you notice in Figure 9, the first picture there, if you let u equal to some constant, u sub 0, and let v vary, then you're going to have a line there in that domain, and that's going to then the points that go with that line are going to trace out a curve, C1, on the surface. Similarly, if you let v equal constant, you'll have another line in your UV plane, and that's going to trace out another curve, C2, on the surface. Well, if you want to find the tangent vectors to the point P sub 0, tangent vectors to C1 and C2, all you need to do is compute the derivative vectors. So, for instance, the tangent vector, let me see if I can highlight it here, one moment. Hold on, class. Yeah. The tangent vector at C1, the tangent vector to the curve C1 to the point P sub 0 is obtained by taking the partial derivative vector of R with respect to V. Because again, that C1 curve is found by, let me see here, one moment. Yeah, you're letting u be a constant. Okay, you're letting u be a constant, so that traces out the space curve C1. If we want a derivative of the space curve C1 at the point P sub 0, we just take the derivative of our vector function of two variables, keeping the u variable fixed. Okay, so again, if we want an equation of a plane, we need a point on the plane and a normal vector. So what we're going to do is we're going to find two vectors in the plane, these two tangent vectors in the plane, and then we'll take the cross product of them. So the vector function r sub v, which is the derivative of the vector function with respect to v, is one of those tangent vectors. Similarly, the derivative vector with respect to u is another one of the tangent vectors, and again that would be the tangent vector where you see it there in figure 9 in the picture, r sub v, that's the tangent vector to the point C1. So I might have had C1 and C2 switched, but the idea is okay. So let's see here. Let me just, one moment here. Yeah, so if you keep U constant, okay, yeah, then you get the grid curve C1, which I think is what I said, right? And if you keep the V constant, you get grid curve C2, which is also what I said. So, okay, yeah, that's right. So the derivative vector with respect to U is the tangent vector for C2, and the derivative vector with respect to V is the tangent vector for C1. That's right, that's right. So now all we need to do, now that we know those two tangent vectors, we just need to evaluate them and then take the cross product. Okay, so let's look at an example here. Example 7, they want you to find the tangent plane to the surface with those parametric equations at the point 113. At the point 113. So first of all, if we're at the point 113, what are our values of U and V? What are the values of U and V if we are at the point 113? If x equals 1, y equals 1, z equals 3. That's right, Charles. U has to be equal to 1 and V has to be equal to 1. That's obvious, just by, thinking it out there and looking at the parametric equations. So they compute the tangent vectors, okay, which you know how to do. You know how to compute tangent vectors. They compute the two tangent vectors, r sub u, r sub v, okay, and then the normal vector to the tangent plane would be the cross product. Okay, so hold on. There's the two tangent vectors. I mean, are there? Hold on. Let me just bring this up a little bit. Are there any questions on those tangent vectors? How they got them? Okay. Well, next step is to then take the cross product of the two tangent vectors, which they do here. So, okay. Now what they do is they say, notice that the point 113, and that's right there below the box, notice the point 113 corresponds to parameter values u equals 1 and v equals 1. So the normal vector there is going to be negative 2i minus 4j plus 4k. Okay, so now all you need to do, you have the normal vector to the plane, and you know a point on the plane. So it's easy to get the equation of the plane. But are there any questions so far? Okay, well then let me continue. Okay, so this is going to be then your equation for your plane. I mean, it's truly fascinating. And they have a picture here. They have a picture of this parametric surface, okay, and the tangent plane. So obviously what they did was they used a program like MATLAB to draw the parametric surface and the tangent plane. And of course, I'm thinking about, when you do your homework and your next exam. Of course, I haven't, I'm still working on the first exam now, getting the grading done and all that. But your second exam is going to be next Wednesday, right? July 7th. That's when the exam will get posted in the evening. And I think to myself, well, it would be nice if my students, when they did a problem like this, if they could graphically check to see if their answer's right. I mean, if your answer's right, you should have a tangent plane to the surface, right, at a point. So on that note, let me show you in Blackboard. I have a program to show you. You see here, I just got to get in Blackboard here. Hold on here. Let me just change this. Let's see, we're not in yet. Hold on, wait, or are we in? Hold on. Yeah, there we are. Okay, so there we are. Go to, can everybody see the Blackboard page okay? Maybe give me a thumbs up if you're seeing it all right. Okay, Charles is seeing it all right, good. And Malik and Ellie, excellent, excellent, thank you. Well, go to MATLAB Programs, click here, and section 11.4, there's a MATLAB program in 11.4 that will help you graph a tangent plane to a parametric surface. And it actually goes with this example 7. So if you click on that, it'll download the program, okay? And now, of course, for your exam, I'm going to be putting these MATLAB programs, I'm going to be writing them in, converting them to Word. So, you'll have to copy, that way when you do Examity, they can, you can download the program so they can download them for you, and there won't be any issue in opening up a Microsoft Word file. So, but if you click on it here, yeah, it'll open it up as an M file. And now go to MATLAB, and let me see here. Let me get it in MATLAB. Okay, and this is what you should see. How many are seeing this when they click on it? Click on that program. Is it bringing this up for you? Okay, Juliana has it. Ellie has it. Excellent. Thank you. Okay, so traditionally what I like to do, as you know, is I like to copy my code. Oh yeah, let me do clear vars, CA clear variables, so there aren't any old variables hanging around that might interfere with my program. And I will copy and paste this in, hit enter. Okay, and you do it too. And let's see what you get. Okay, are you getting something like this? Who's getting something like that? I see I have a surface and a plane. Okay, Ellie's seeing that. Good. And if you go to, and Juliana is, excellent. Now, if you go to Tools, if you do Rotate 3D, I wanna kind of check to see the tangent, that this plane is tangent to the surface. So I got to kind of might have to rotate the figure a little bit to see that it is tangent. And that's pretty good, right? Pretty good. I'm happy with what I see there. So see, that's a graphical reinforcement that your answer was right. You have a graphical, you've confirmed it graphically now, your answer. How many think that's pretty awesome? Pretty cool. Get that a little better here. There we go. All right, so are there any, how many think this is kind of a cool thing you've learned? A nice thing in section 11.4. Okay, thank you, Ellie. I hope more than Ellie likes it, but Okay, thank you, Juliana. All right, are there any questions at all? Okay, I'm going to stop the recording.